Okay, we're starting. So we're going to continue with 1.3 algebraic expressions and factoring. Already started factoring. Let's talk about the Gcf idea. Let's start by righting a wrong. Some things I wanted to find that we never really defined last time. I guess I got excited and went off on a few tangents. But wanted to find the term an algebraic, in parentheses, don't normally say that all the time, expression. Okay. So we mentioned what a term was. It was very vague. It was essentially a product. So you have a bunch of things multiplying together. We consider that one thing, and that mass is called a term. It's kind of like a molecule from chemistry. You know, you have all these atoms and come together and make a compound, and you're like, oh, that's a compound. Well, that's an algebraic expression from a mathematical point of view. So this is a combination of terms via the arithmetic operations. So that's like addition, subtraction, multiplication, division, turning things into radicals, that sort of thing. And composition, which is something that we'll talk about again, but that's basically when you take one thing and plug it inside of another thing. You say you've composed them. A little bit more specifically, by the end of this class, you will be familiar with all of these kinds of things. There are the so-called elementary functions. Most people go through their mathematical career and never see things other than these guys. They're very elementary. They kind of like another chemistry example, they are like our periodic table. Pretty much every mathematical expression we build will be built up of these guys, so you need to understand them. There are 6 of them. Kind of like how there are 6 infinity stones. Right? These form your reality, and they can control everything in your mathematical universe. The infinity gauntlet is algebra skills. If you have algebra skills and you know about these 6 things, you can do anything in elementary mathematics. The polynomials were the first one. I specifically defined them last time. So these are a class of functions, and they're like an elementary building block as far as we're concerned. They're a very fundamental part of our reality. The other thing is the radical functions. We also talk about them, spoke about them. It just means when you raise something to a fractional power instead of a positive whole number power. There are the rational functions. We'll do a section on them. The root word is ratio. It means when you divide 2 functions, usually we're talking about 2 polynomials, you divide them and call that a rational function. Like x plus 1 divided by x plus 2. That function is a rational function. There are the trig functions. The guys that you learn about from trigonometry, sine, cosine, tangent, cotangent, cosecant, secant, all of those guys. There are also the exponential functions. We spoke about the laws of exponents before, but we're going to talk about when you actually create a function with an exponent. So in the power, there's a variable, and the power is changing. You create what you call an exponential function. We'll talk about that. And we'll also talk about logarithms. Functions. These are the inverse of the exponential functions. We'll talk about in detail about that. Most people know about the first 5. Some people before they hit pre-calc have also seen logarithmic functions, but probably not, so I'm going to introduce those to you when we finally talk about them. But yeah, these 6 functions, the arithmetic operations and the composition, everything you're doing is built out of these, and so all you have to do is learn the rules that govern these 6 functions and these operations, and you've kind of got it in the bag once you do a little bit of practice with it. And so we can think of an algebraic expression, which is probably a bad name for it because in higher mathematics algebraic means something else. Is some combination of perhaps some of the above 6 functions. Via arithmetic and composition. Okay, so that's an algebraic expression. So, for example, we can create something that is in neither class really, and whatever we create using these classes of functions, we call that just a more general algebraic expression. So I can talk about a polynomial, right? So it's like x plus 1 is a polynomial, like x squared minus 2 is a polynomial. But then you can also talk about the rational functions. This is what you create when you divide 2 polynomials. So you like this and you do that. That's called a rational function. But what if you decided to take a radical function, like the square root of x, and you decide to, you know what, I'm going to take that and plug it in the place of x, and you create something, you combine these two, and you create something like radical x plus 1 over x squared minus 1. Now, technically, that does not fit the definition of a polynomial, and it does not fit the definition of a rational function. It's something else entirely. However, it was created by combining 3 types, right? So this kind of expression here is what we refer to as algebraic expression. And sometimes just leave it out, we just call it an expression. So you have these kinds of functions, you mix and match them using arithmetic or composition by plugging one into the other, you create what we call an algebraic expression, right? And pretty much everything you're doing in math class is going to be you dealing with some sort of expression. And to deal with an expression in the general sense, what you really need to understand is how each particular component that is plugged into that expression, how does it behave individually? And that's going to give you a lot of insight on how you want to deal with that entire expression as a whole. Find out how the components were made up, and you can deal with it. So that's an algebraic expression. Okay? And yeah, for years and years you're studying math, you'll never really see any functions that's not accounted for here. Now, another type of thing that we want to talk about is an equation. An expression. 2 or more expressions may be connected by an, we call it an equal sign, and that's the guy that looks like this. Just 2 horizontal bars to create a different kind of expression called an equation. Now, I do want you to think of these as different things, even though, again, it's just a mixture or a connection. So something like A equals B, where A and B are expressions. So you can take a bunch of things that you combined and you can put them on either side and connect them with this symbol. And that, we say you've created an equation. Okay? Now, without the equal sign, it's an expression. With the equal sign, it's an equation. And the statement A equals B means A and B will have the same outputs when set values for the variables are chosen. Or the equation becomes, so in this particular case we call this, we would call the equation in this case an identity. Or the equation becomes a true statement. So I can say something like x squared minus 4 equals x minus 2 times x plus 2. This is me writing down an equation. This equation is in fact an identity. Both sides will always give me the same thing when I plug in a particular x value. Right? So if I plug in x equals 1 over here and x equals 1 over there and I compute the values, they'll always give me the same value all the time. I can also write down something like x plus 1 equals 3. And this becomes a true statement for a particular value of x. Which is the variable, which we just define what that is. And this one you just call a regular equation. So if someone mentions an identity, they mean, here's an equation that's always true. Every time you plug in a value, both sides are going to give you the same answer. Then you have equations that they might not always be true, but there are some values that you can plug in for x. So for example here, x equals 2 will make both sides give you the same value. Okay? And that's the difference between an equation versus an identity. Now, here is what's important. Decisions. Okay. The presence or lack thereof of an equal sign indicates the legal math moves you can do. That is very important. It's an indication of certain things are now allowed versus not allowed. So we'll talk about this more when we talk about equations. I'm actually going to go back to us solving equations. So for example, if you see x equals 2, then doing something like squaring everything, to get x squared equals 4 is legal. Versus if you just saw the radical of x minus 2 and you just decide you know what, I don't like how that looks, I'm going to square it. This is illegal. Right? You can't just take an expression and decide to square it. So the fact that there's an equal sign versus no equal sign, it indicates certain things. Certain things are allowed, certain things are not allowed. Right? So you can manipulate equation in very specific ways, and I'm going to talk about what those ways are. If the equal sign is not present, the same things that you could do over here are no longer allowed over here. Expressions and equations are, I want you to think of them as different things. If I see an equal sign, certain things are allowed. If I don't see it, certain things aren't allowed. So, see an equal sign, I can square both sides. I can square everything all I want, right? It's not going to really change anything. It won't put you in a bad situation. But if you don't see an equal sign and you decide, oh, I'm going to square, you've now changed the value of the thing, right? So, if I write down the number 4, okay, I'm going to square it. Well, now it's a 16. It's not a 4 anymore, right? You changed the situation. You altered the reality, which in a bad way, right? However, if I said, you know, x equals 2, and then I square both sides, and then I would say x squared equals 4, well, that's still a true statement, because if I plug in 2 here, it still works, right? As opposed to here, if I were to plug in, say, 6, this is going to output me 2, whereas if I square it and plug in 6, now it outputs me what? 4, right? It gives me a different output. So this is a different expression from that. They should not be considered the same. So if you want to consider them the same, you're not allowed to do certain things. That's important. There are a bunch of things you can do, like you can multiply and divide by the same thing, that would be allowed. But like randomly squaring or just randomly multiplying, not allowed. Okay? So that's very important. This, you want to think of it as a sign. Hey, certain things are allowed, certain things aren't allowed. You really want to think of them separately in your head. And I guess another tip here is to just a general tip here. Practice. This helps you in math, helps you with everything. Practice awareness. Okay, that is going to be very important. You should be aware of the fact that there's an equal sign here. It shouldn't be something that goes without noticing. So a lot of people they do all these things because they don't even notice that they're not in the situation to do the thing. Right? To them it's just, oh, squaring is just something that happens whatever, right? No, it doesn't. Squaring is something that can happen in specific instances, and it cannot happen in other specific instances. Don't just think of, oh, squaring is a thing, I can do whatever I want. It is not. Right? You have to be aware of the situation you're in, be aware of all the rules governing the situation, and make sure that you follow the rules, or you're prepared to face the consequences if you don't follow the rules. This reminds me, today I was, again, going up the stairs, and there was a bunch of people was so slow, and I was walking up, and then I was like, I should have gone up the stairs that marked down. You know, I was messing with you guys last time, but I don't want you to think that I'm here to tell you how to live your lives and you should obey all the rules. That's not actually the point. Here, as a teacher, here's what I want for you guys more than anything. I want you to just be aware of the rules, right? Every time you follow a rule or you don't follow one, I want you to do it consciously. I want you to understand, this is a rule and I'm deliberately choosing to break it. I don't want you to just run up the stairs that are marked down just because, oh, I just did it, I don't know why I did it, right? No, you're supposed to approach the stairs and you're supposed to notice, okay, this one's marked up, that one is marked down. However, that's empty, this is full. I know this is against the rules, but I'm going to choose to do that anyway, because at this point in time, it is more important for me to get to class on time than it is to obey the rule, right? I want that thought process to go through your head, right? So I'm not just saying you have to act a certain way. And by the way, this doesn't absolve you. Don't go around breaking rules and say, Jhevon said it was okay as long as I was aware of what I was doing. That's not going to help you. That's not what I'm saying. But you need to practice the awareness. Never do something for a random just because reason. Always know why you're doing something, right? You're running up the wrong stairwell, you should be aware that you're doing it. And you should know, yeah, I know this is the wrong stairwell, but I'm doing it anyway. right? It should be a conscious decision, right? So just like that, not practicing that gets you in trouble with situations here. People are just like, I don't like the radical, I can just square it. They never really think, no, it's not, they're not aware that it's not a thing. And so when I'm telling you all these rules and definitions, a part of it is to help you in this activity right here, practice awareness. It's very important. Just be aware of the notations and the symbols, be aware of what they mean, and be aware of what is allowed versus not allowed. And whenever you take a step, it should always be a conscious decision. Now, eventually, you'll make these decisions so often that it becomes automatic, right? So it's kind of like when you're learning to walk, you have to consciously think, left foot or right foot, right? Or you're learning to drive, you have to consciously think, I have to look in my mirrors all the time. Eventually you're driving, you can be eating a hamburger, doing your makeup, doing all sorts of things, talking to your friend on the speakerphone, and you're driving anyway, and you're still actually paying attention without you having to think about it. So that's where you kind of want to get. But in the beginning, you want to be very careful and tiptoe around the rules, make sure you understand how they work and what the consequences are. So be sure to do that. So every time I'm writing something down, even if I'm writing something down that you've seen 1,000 times, I want you to look at it again and really understand. Yes, I know you've seen that 1,000,000 times. I'm telling you again what it means specifically. And I'm telling you, when he shows up, certain things are allowed. When he doesn't show up, certain things are not allowed. I want you to think about that carefully. Okay. So yeah, algebraic expressions and equations, these are two important things, and they matter. The differences between these two, they matter a lot. So let's pick up with factoring. We looked at the Gcf factoring last time. We did like 2 examples, I think. Do I want to do some more? Yeah, let's quickly do something. Just to get us back into the groove, slowly. Factor the following. Let's jump into this first one. What do you think? Yeah? Great. 4 is a common term. This is in fact the GCF. That one is easy. So you just pull it out and you write what's left over on the inside. And again, I want you to remember what that actually means is that technically speaking, what actually happens is when you pull out the 4 to the 1, what happens is that the 4 is on the inside, you subtracted the power that you pulled out, right? So you had the x squared and the plus sign here, but what happened to the actual individuals that were there in the first place? You subtracted the powers that you pull out. You'd result in 4 to the zeros in both cases, which result in becoming 1 at the end of the day, right? So again, be aware that that's what actually happens. Now, for something simple like this, you don't have to think about it, but at least in the beginning, be aware that that's what's happening. Because now, when you get to a harder situation, like someone throws fractions in the power, it doesn't stump you. You know exactly how to deal with it, right? That was the example we had ended on last time. So factoring out of GCF, it always works the same way. It doesn't matter if the thing looks scary or not. It's always going to be the same thing. Pull out the common factor, subtract the powers from the things you pull out. That will always be how you do it in all situations. Just because the situation looks different doesn't mean it is different. Factoring is factoring. Yeah.
I have an example. Can you do 2? Is this 2x plus 2? Or something?
Can you do like 2 and then do 2x squared plus 2?
Yeah.
Now, in one sense, it is legal. That's not wrong. In another sense, it's not complete. Because what it means is that 2 is still a common term, right? Which means you could do this and someone could do it and they could just do what you just did again, right? You don't want that kind of situation, right? So that's like your mom asking you to do the dishes and you won't wash half of them. It's like, well, now I'm gonna have to do the rest of it, right? You haven't really washed the dishes, right? You took some action, it was the right action, but you never completed it, you never followed through. So this isn't wrong, but it wouldn't be considered fully factored. So if the instructor says factor completely, this wouldn't get full credit, even though it's not wrong. It's on the way. So you do want to find the GCF, it's the greatest common factor, meaning you want to pull out the largest power of 2 that's possible to pull out. 4 is 2 squared, this is 2 squared. You pulled out a 2 to the 1. It was not, in fact, the largest power of 2 that you could have pulled out. So technically, while not wrong, you didn't actually pull out the GCF. You always pull out the greatest power possible. So E. Okay, so what would we do here? Yeah?
I pulled out 2y.
2y?
Parentheses. X squared plus 2xy minus x squared y.
Okay. You guys agree?
Yeah.
Why not? What's wrong? Yeah. Right, now notice that if you look back here, x is something that's in every term, right? Which means 2y wasn't the GCF because we still have a common thing left over. So remember what you do? You go through, you identify all the common terms. Notice here the 4 we can think of as like a 2 squared. So 2 is in everyone, right? And then you're going to identify, oh, there's also an x is in everyone. And then you're going to identify, oh, a y is in everyone. Your GCF should have 3 things in it, right? So there's going to be the 2, and then you're going to decide, what is the power I can pull out? Right? And it's just a bad thing about language here. You want to pull out the largest possible thing, which is in fact going to be the smallest power. Because that's what you can pull out without creating a fraction. So now 2 shows up here to the power 1, 2 shows up here to the power 2, 2 shows up here to the power 1. You're going to pick the smallest guy, which is 2 to the power 1. That's what gets pulled out. Then you know there should also be an x, and that deals with the green part. Then there's also an x. What are the powers here? 2, there's a power 1 here, there's a power 2 here. 1 is the smallest power, so I'm going to pull out power 1. That's the second part. Then lastly, there is a y. The third thing. Now what are the powers that appears to? Well, there's a power 1, there's a power 2, there's a power 2, so I'm going to pull out the power 1 and put out the lowest power. So 2xy is going to be the GCF. And now I'm going to write what's left inside. Now, that just means technically what's happening is I'm subtracting 1 power from all the 2's that appear. So that 2 is going to disappear. This 2 is going to still have 1 left, so he's going to show up in the middle. This 2 is going to disappear. I'm pulling out, subtracting 1 from all the x's. So I have an x left here. This x will disappear, and I'll have an x left here. I'm pulling out 1 from all the y's, so this guy's going to disappear. There's going to be 1 left over here and 1 left over here. And at the end of the day, we are going to have x is the only thing that's going to be left, because the 2 to the 1 and y to the 1, I moved them out, and I only moved out 1 factor of x, so there's 1 left. Plus, now 2 is going to be left, the x is gone, and 1 of the y's are still there, minus x, y is going to be left here. Now you'll notice that there's nothing that's in every one again. Right? So if I talk about x, it's in these two, but not in the middle. Talk about 2, it's only in the middle term. Talk about y, it's in these two, but not in the third. Right? So you've in fact factored out the GCF, and that's going to be the answer. Now I know a lot more thought went into that than you're probably used to, but again, the first few times you do it, you really want to think slowly and understand what you're doing. Pretty soon you'll be doing it while doing other things, and it won't be a big deal. But also, if you just practice it fast and you never really learn the rules, it'll turn out you'll learn to do the wrong thing just as easily, and you're not going to realize that it's the wrong thing until after you get your grade back. You're going to feel like, yeah, I killed it on that test, and then you get back a bad grade. Like, what happened? You're going to get so good at doing the wrong thing, it's going to feel like the right thing, right? Right and wrong really is just a matter of habit, right? If you kept doing the wrong thing, it's going to start to feel right. It becomes easier to do it the next time. And that's why people can go in an exam, yeah, man, you did great. And then they actually didn't do great. Why was there a disconnect between their emotional feeling and the actual grade? It was because their emotional feeling was based on doing the wrong thing multiple times over, right? You don't want to get into that trap. So think slowly, make sure you know what you're doing. You're aware, this is how it works. This is how it works. This is how it works. After 20 times of doing that, it becomes natural to do it again, right? See. What's the GCF here? X plus C. So that's the only common term. You might say, what about the X? Well, there's none in that guy, right? What about the Y? Well, there's none in that guy. What about the Z? There's none in this. So X plus Z is the only common term. You're going to pull that out. And you can double check. Should always double check, make sure that nothing is actually common anymore, and that's good enough for us right now. Okay. Now, second technique, factor by grouping. Okay, so factor by grouping usually comes in GCF is always going to be the first thing. I'm actually going to give you a strategy to factoring to wrap this section up. Kind of things you should be doing first, second, third, etc. Trying to factor out a GCF is always going to be the first thing you're thinking of. But if there is no GCF and you already factor it out and you're left over with 4 things left over, once there are 4 or more things, that's a hint to you. It can work in other situations, but these are by far the most common situation. 99.9% of the time where a factor by grouping is going to work out, there are going to be 4 or more guys to make it work out. Here's the process. And this is the process if it works. It's not guaranteed to work, but it is something you should think about. Pair of terms. So that's the first thing. 2. Factor out Gcf from each pair. 3. What is left over in parentheses should be the same. Now, if it's not the same, what it means is that this technique actually wasn't the right one. Right, now when the two terms that are left over is the same, what you'll notice that you've just done, based on the definition, is you've literally created another GCF. And this is called factor by grouping. Grouping because you kind of create mini groups, usually pairs. There are exceptions, but in pre-calc it's usually going to be pairs. Yeah, let's do some examples. We'll be practicing more factor by grouping in the next section as well, so I'll only do 2 examples here. So factor. Copied something down wrong. Try this too. So just to show you how this thing works. Here you have 4 things. What we're going to do, that makes it kind of silly because you can factor these off. Bump up the powers here by 1 more. Now everyone's a different power. That's just to make it not a silly example, because technically I could have just added these 2 here and do something else. But now this becomes valid, a valid technique, instead of just a silly example. So now what you realize is that, yeah, x is a GCF. Pretty much going to ignore that at the moment, but the 5 and the 2 creates a situation where there's not a 5 in everyone, and there's not a 2 in everyone. So those aren't common. What you can try here is to pair things off. Right, so you think of it in pairs. So this is why it's called factor by grouping. You'll create a little bit of groups, both groups. And then what you're going to do within each group is factor out the GCF, right? Because it'll have GCFs in each one. What's the GCF in the first one? 5x. So if I were to factor out 5x, what would I be left over with here? X plus 1. Now, what is the GCF over here? 2x cubed. And if I were to factor out the 2x cubed, I would still be left with x plus 1. Now what you realize what happened is, these now, if you look at the thing as a whole, this is a new GCF. Right? This must happen for this technique to even be valid. Otherwise, try a different technique, or just make sure you actually factor in correctly. Try a different technique. For you to actually be able to complete this technique, you must create a new GCF by doing these little mini group factors. So now what happens is that you can actually factor out, in fact it's a little bit bigger because you can get an extra x out here. You're going to factor out the new GCF that was created, which in this case is going to be an x times an x plus 1. And then you're going to write what's left over on the inside. So the 5 wasn't taken out, so he stays. The x I took him out, okay, the x plus 1 I took him out, so that's all that's left in the first term, so I put back the plus sign. The 2 wasn't taken out, so he stays. There were 3 factors of x, I took out 1 factor of x, so there are 2 factors of x left. You can also think of this as me just subtracting the power 1 from the power 3. And the x plus 1 I pulled out, so there's no one else left. There is just this. And that is fully factored, right? So there are times when you have 4 more terms, you can kind of group them together, pull out common factors from each part, and then doing so, if it creates a new GCF, this was a good technique to try. You pull out the new GCF, and you'd be able to factor something even further. So you see something like that. That is not as silly because literally no one is in everyone at the moment. So there's not an x in everything, there's not a 5 in everything, there's not a y in everything. So right now, factoring out the GCF doesn't seem to do anything at the moment. So what you might think is, let's just group these guys. And you can then, what is the GCF here? 5, that's a common term in everyone. What would you be left over with? X plus y plus common term here. Well, x, what would you be left over with? X plus y. Now you realize, oh, that's another common term. Do a GCF factoring again in general now. So the x plus y will come out, and I'd be left over with the 5 plus the x. And so that would be the factor here. One thing I want you to be aware of, even though it might seem totally weird, because sometimes we're going to talk about this when I look at the AC method. Sometimes we might not have a situation to factor by grouping, but we'll create one. And sometimes in doing so, students kind of worry about, what if I do it the wrong way? There's no wrong way to do it. So I want you to note here the order of the terms don't matter at the start of this process.
still processing.
Okay. What do I mean? If there was some other rearrangement, it wouldn't actually matter. So there are a lot of ways you can rearrange 4 terms, but let me just show you a random rearrangement. Let's say the order of these two were switched for whatever reason. So I had 5x plus x squared plus 5y plus xy, right? Same 4 terms in a different order, right? Let's say someone decides to write it down in this order again. You can still do Gcf Factoring. Common term here would be what? What would you left over with? 5 plus x. Common term here? Y. What do you left over? 5 plus x. You end up with a Gcf again. Now if you factor out that Gcf, what happens? Well, you'd be left with 5 plus x times what's left over, x plus y. Notice you get exactly the same thing because multiplication we know works in any order. So the order that you write them down in is not going to matter. Once Gcf factoring can work, it'll work in any order, right? I can do the 5x squared, the 5x plus the xy plus the 5y plus the x squared. Right? And what's going to happen now? Did I write down the right things? Five x, xy, 5y, x squared. Okay, so now if we look at this guy here, what's the GCF here? X, 5 plus x. What about this? There's 1, right? So here we have 5y plus x squared. Now what are you going to do here? Nothing, there's not the same. So what you would do is you would try to, because remember that for the method to work, you need to have the same thing inside the parentheses. So when this happens, it either means you made a mistake or you need to somehow arrange things to make sure they get the same values. But within the what?
5 plus y. 5 plus y.
There's no.
Oh, yes. Right, which we still don't get the same, right? So you want to make sure that in order to finish here, because not the same thing. What's that in proper grammar? Not the same thing is left over in parentheses. Now we will do some examples where factoring out a 1 is actually fine for what's there, but you want to make sure that when you fit for this thing to work out, the arrangement must be such that the thing left over in brackets after you pull things out is the same. And sometimes it will work with multiple rearrangements. Sometimes you just have to try another thing. But this is something you think about when you have 4 terms. Let's move on to the next thing. I want to get to factoring trinomials. Where one method is going to use factor by grouping, so that's why I wanted to do this first. This is the third thing. Now, remember what I told you a trinomial was? It was just a polynomial with 3 terms in it. Now, the polynomials are nice because once you learn the basics with them, it's kind of easy to generalize it to other kinds of functions. So we want to factor expressions of the type. Now type is loosely used here, but we'll talk about that soon, later. Something like ax squared plus bx plus c. Okay? And there are two main cases here. One is when your a is equal to 1, and 2, when your a is not equal to 1. And the techniques are slightly different based on one or the other. So let's look at case 1. Now case 1 takes you noticing a certain pattern. If you have x plus a times x plus b, then we can apply the distributive law. Multiply everybody out, so that would be x squared plus bx. Multiply everyone out, that's ax plus ab. If you group like terms, you'll notice that this is what you have. And so now you notice a little pattern here that we're going to take advantage of. Notice that this here is the product of the two numbers. And this here is the sum of the numbers. So if you see a situation like this, one way to actually try to factor it, factor means you're going from this situation up, remember that's factoring. And expanding is going from this situation down. It's expanding. Okay. So when you see something like this, which is expanded, we just have a bunch of things being added together. And I want to go to a situation where it's contracted. There's a bunch of things multiplying each other. One pattern you can look for is if the middle term is the sum of two numbers and the last term is the multiplication of two numbers, and you're going to try to recreate this situation by pulling it backwards. So given something like x squared plus bx plus c, try to think of two numbers that multiply to give c and sum to give e. Say R1, R2 are the numbers, then factoring gives x plus R1 times x plus R2. Let's just do a few examples to explain what I mean by that phrase. And none of these techniques really work in all cases, so sometimes I want to show you cases where they don't work out, so it's not going to work out for this one. But it doesn't mean you're stuck, like there are other methods. And this again, I feel like factor and quadratics is something a lot of people are familiar with, so I'm just going to jump into these real quick. So, we see this. Things that should go through your head. The first thing is notice 1 is the coefficient of x squared. Once you notice that, then you're going to think of two numbers that multiply to give 6. And more specifically, you do want to consider the signs that are involved and add to give positive 5. Can you think of such numbers? Two and 3, right? When you think of that, you get excited. 2 and 3 are the numbers. Yes! Okay, yeah. No, if I multiply these two, 2 times 3, I would get 6. If I add 2 and 3, I actually get 5. So the result of that is, on paper, someone would just jump in and write this down, x, x, and specifically plus 2 and plus 3 work. So you're going to put plus 2 and plus 3. So this number goes here, that number goes there, right? And that would be the factor, right? You realize that if you were to multiply this out, you'll always get that back, right? So it's 2 lines, but like at least 3 things go through your head before those 2 lines. Notice that there's a 1 in front. That allows you to do this trick where you just think of 2 numbers that multiply to give that and add to give that. Once you find the numbers, open 2 brackets and arrange it this way, and that will always be the factor. So this is 1. Can we think of 2 numbers that when I multiply I get positive 1, when I add them I get positive 2? 1 and 1. So I'm just going to have plus 1 and plus 1. Notice I have the same thing. Customarily we just would like to write this as that squared. You can also notice that that was in the form of a perfect square, but you know, I think it's just easier to think of it this way. Okay, how are you going to do this one? So you open this. You want to think of 2 numbers that multiply to give you minus 12. There are a couple ways you can think about this question, but for one of them, you can just ignore the fact that there are y's there for a second and put them back at the end. So that's one thing you can do. Or in the other one, you can just think of the y itself as just some other number. So one way you can think of it is, can I find 2 numbers that when I multiply them I get minus 12y squared, and when I add them I get y, right? So obviously the 2 numbers must have y's attached to them so that when I multiply them I get a y squared. And so now really the focus is on the coefficients, right? What numbers multiply to get minus 12, and when I add them I get plus 1, right? So you end up thinking along the same lines. So you start out by putting the x's here. What are the numbers? Negative 3 and a plus 4, right? So that's what I would put in. Negative 3 and a plus 4. Now, if you're the person who just decided I'm going to ignore the y's for a second, what you would do is you now just put them back, attach them to the ends. And what you'd realize is that when you multiply these 2, you'll get the y squared, but when you add them, you'll get that. And that's actually the factor for that. Now, this method doesn't always work. So like in B, so here you start to think 2 numbers that multiply to give 7 and some minus 7, and some to give 1. And the thing is, 7 is prime. So really the only choices are 1 and 7. Right? It's either 1 times 7 or 7 times 1. Either minus 1 times a positive 7 or minus 7 times a positive 1. And you realize, I can't get these won't add to 1. From any arrangement. So that won't work. But otherwise, when you see 3 terms, one thing squared, one thing not squared, and the thing not in the third, you kind of play this little game. Can I think of 2 numbers that multiplies to give this guy over here and adds to give that guy over there? Now, once you can actually do that, you can factor in this way. And once you can't do that, you would try something else. We're going to look at other situations. Let's see if I can at least get ahead on the next case. Case 2. This is when your a is not equal to 1. So 2 methods here. Second one is not going to sound like a method, but next time I'll describe it and it'll be a method. At least I want to get through the AC method. And the second one, trial and error. But it doesn't sound like a method, but the way I'm going to show you, it's actually going to be something that you can get good at with practice. And if you get good at it enough, it'll be much faster than this one. You can do a lot of things in your head, and someone's going to wonder, how do you do that so fast? But for now, there's a standard procedure on how to attack this situation called the AC method. It's the kind of brain dead method when you don't want to do too much thinking. Let's talk about the AC method. So to factor one, find AC. That's why it's called the AC method. You're going to take the number here, you're going to multiply the number there. You're going to create another number. 2. You're actually going to play a similar game now to the previous case. You want to find 2 numbers that multiply to give AC and add to give the middle term, the middle coefficient. This is B. 3. Split the middle term. Into these 2 numbers. And then 4, factor by grouping, which we covered just before this. This is called the AC method. So it reduces the case where a is not equal to 1 to be very similar to the case where a equals 1. Because you have to essentially play the same game in step 2. Except you have to play with a larger number. You have to play with the number AC. Let's give you some examples here. And next time I'll probably go over these with the trial and error method or whatever. So you want to factor those. So let me just quickly show you how the AC method is going to look like for the first example, and maybe we can do the second example together. So I'm going to go through these 4 steps. So, A. So 1. Notice coefficient of x squared is not 1. So the second thing that goes to your mind is think of the AC method, or trial and error. Of course, the focus here is the AC method. So we're gonna, let's say I think of the AC method. So I look at this, I want to factor it. Oh, it's not 1. Next thought, I should use the AC method. So the next thing I'm going to do is I'm going to find AC. Now AC is going to just be this times that. So that's going to be 2 times 2 equals 4. So that's your AC. Now what you're going to do is you want to break that up into 2 numbers. Right? You want to break it up into numbers that when you multiply them you get AC, which means you multiply them you get 4, and when you add them you get plus 5. Can you think of that numbers? Well, 2 and 2 won't work. 2 and 2 multiplies to give 4, but they don't add to give 5. 1 and 4 would work. Multiply these 2, so these multiply to give AC, and they add to give 5. Right? So I found those 2 numbers. Right? Now this all happens in your head for the most part. You don't really write this down on the paper. But now you start to write things down on paper. Here's the first thing you write down. You're going to split the middle term into these 2. So the next line is going to be 2x squared plus 4x plus 1x plus 2. Okay. So the middle term, the 5, now splits into those 2. And now what you're going to do is you're going to factor by grouping. So you're going to pair these guys off and factor out the common term. So what's the common term between these 2? 2x. What's left over?
X plus
Plus 2. Common term between these 2? 1. So I pull out a 1. What am I left over with? Well, x plus 2. Now x plus 2, as you notice, you've just created another common term. So you're going to pull that out. And that's the factor. Right? And again, if you wrote it in the other order, I don't want you to worry too much. That means you'd have 2x squared. Let's say you decide to write down the 1x first and then write down the 4x. It's still going to work out. Common term here, x, you'd be left over with 2x plus 1. Common term here, 2. You'd be left over with 2x plus 1. You still create the GCF, 2x plus 1. Factor that out. It still factors. Right? So this method is called the AC method. Try the other 2 examples. We'll do a few more next time. I will see you guys on Monday, where we have a quiz. So know everything up to here.